This is Xenofeed, news of the outworld.
For centuries, humanity has gazed at the stars and wondered, are we alone? However, while the search for extraterrestrial life often focuses on distant exoplanets, some of the most promising places to find life might be right here in our own solar system. From the icy moons of Jupiter and Saturn to the dusty plains of Mars and the mysterious clouds of Venus, scientists are uncovering tantalizing clues that life, perhaps microbial, perhaps more, could exist closer to home than we ever imagined. Join us as we explore the 9 most likely candidates for life in our cosmic backyard. Mars has long captivated our imagination as a potential abode for life. Recent discoveries have only deepened this intrigue. NASA's Perseverance rover is currently exploring Jezero Crater, an ancient lake bed that may have once teemed with microbial life. The rover has already detected organic molecules, the building blocks of life, in Martian rocks. Meanwhile, the European Space Agency's ExoMars program aims to drill beneath the surface, where liquid water might still exist, shielded from harsh radiation. Mars has several features that make it a prime candidate for the search for life, such as ancient river valleys and lake beds. These geological features suggest that liquid water once flowed on the surface of Mars, creating environments that could have supported life. Mars has hydrated minerals that have chemically bound water within their structure that indicates water was present on Mars for extended periods. Mars also contains a huge reservoir of subsurface ice. Large amounts of water ice have been detected beneath the surface, particularly at the poles. This ice could potentially melt into liquid water under certain conditions. Methane has also been detected in the Martian atmosphere, and its seasonal variations hint at possible biological or geological processes. On Earth, a significant amount of methane is produced by living organisms. These factors combined make Mars a compelling target for ongoing and future missions aimed at uncovering the secrets of the Red Planet and its potential to harbor life. Beneath the icy crust of Jupiter's moon Europa lies a vast global ocean, one that could hold more than twice the volume of Earth's oceans. This subsurface sea is kept liquid by tidal heating, a process driven by Jupiter's immense gravitational pull. Hydrothermal vents on the ocean floor could offer energy sources similar to those that support life in Earth's deep oceans. Many researchers think Europa's ocean could support microorganisms or even more complex, perhaps even intelligent marine life. On Earth, microbes cluster around hydrothermal vents in dark zones beneath the sea. Similar processes might exist under Europa's crust. NASA's Europa Clipper, launched in 2024, will orbit Jupiter and pass near Europa. Instruments will scan the moon's icy shell and sample water vapor erupting from cracks in Europa's surface. Researchers expect discoveries in the moon's chemistry, signs of organic molecules, or temperature variations hinting at warm regions below the ice. A future lander will descend onto Europa's crust, drill through the ice, capture water samples, and place them into specialized containers for analysis. An epoch-defining moment might arrive if these samples reveal alien cells or compounds unique to living organisms. Saturn's moon Enceladus may be small, but the potential for life there is tremendous. The Cassini spacecraft discovered geysers of water vapor and ice erupting from its south pole, revealing a subsurface ocean rich in organic molecules and hydrogen. These findings suggest that Enceladus has the ingredients for life: water, energy, and chemistry. Much like Europa, the presence of a subsurface ocean beneath Enceladus's icy crust is one of the most compelling reasons to consider it a candidate for life. This ocean is kept warm by tidal heating, which occurs due to the gravitational interactions between Enceladus and Saturn. The ocean is believed to be rich in organic molecules and hydrogen, which are essential for life. Saturn's largest moon, Titan, is a world unlike any other. With its thick atmosphere and lakes of liquid methane and ethane, Titan is a laboratory for prebiotic chemistry. While life as we know it requires water, Titan's unique environment raises the possibility of methane-based life forms. Observations from the Cassini-Huygens mission revealed a dense nitrogen atmosphere and trace hydrocarbons, fostering organic chemistry reminiscent of early Earth. These parallels, coupled with Titan's liquid methane-ethane lakes, create an environment conducive to studying abiotic processes generating precursors to life. Evidence suggests that Titan also sustains a subsurface ocean beneath its ice crust. The ocean, comprised of liquid water mixed with ammonia, offers a rich habitat for water-based biochemical reactions. On the surface, stable methane cycles and photochemical processes yield an array of complex organic materials, including polycyclic aromatic hydrocarbons. These materials drift through Titan's thick skies and descend onto the Moon's terrain, creating a unique setting for potential prebiotic pathways. Future missions, such as NASA's Dragonfly rotorcraft lander set to launch in 2028, plan to explore Titan's diverse landscapes. By collecting surface samples, analyzing atmospheric chemistry, and probing hidden oceans, researchers seek critical insights into life's origins. Titan's abundance of organic molecules, liquid reservoirs, and protective atmosphere make it an excellent candidate for exobiological investigations. Venus is Earth's near twin in mass and diameter, though conditions on its surface differ in extreme ways from that of Earth. A blanket of carbon dioxide extends from ground to sky, and dense layers of sulfuric acid droplets obscure visible light. Temperatures at ground level exceed 460 degrees centigrade, hot enough to melt lead. Atmospheric pressure towers far above pressures on Earth, which creates a crushing environment unsuitable for life as we know it. While Venus's surface is a hellish landscape of crushing pressure and scorching temperatures, its upper atmosphere is surprisingly Earth-like. In 2020, scientists detected phosphine, a potential biosignature in Venus's clouds. While the discovery remains controversial, it has sparked renewed interest in the possibility of airborne microbial life on Venus. Another line of inquiry involves Venus's ancient history. Computer simulations indicate liquid water once covered large regions of the planet. Over eons, a runaway greenhouse effect accelerated, causing oceans to evaporate and the surface to bake. If life appeared during the earlier era, remnants or descendants might have transitioned to aerial niches above the punishing heat. Multiple future missions aim to investigate Venus further. NASA's Da Vinci will drop a specialized probe through the atmosphere and gather data on composition and structure. Europe's Envision orbiter will map geological features, searching for clues about volcanism and possible subsurface activity. Instruments aboard these spacecrafts could measure isotopes, gases, and other markers of life. Even if they uncover only biological processes, Venus will help us understand rocky planet evolution. Ceres sits in the asteroid belt, largest among countless rocky fragments orbiting in the space between Mars and Jupiter. For decades, astronomers gazed at its faint glow and wondered about the possibility of water. Then NASA's Dawn spacecraft arrived. Instruments found unmistakable signs of hydrated minerals on the surface, pointing to interactions with liquid in the past. Bright salt deposits in craters, most famously an Okator crater, reveal chemicals often linked to water-rich environments. Subsurface reservoirs may still exist in pockets there, shielded from solar radiation by thick layers of rock and ice. Scientists propose that these regions contain brines, a highly saline solution, typically composed of water mixed with significant amounts of dissolved salts. This notion of salty, potentially liquid water sparks excitement about microbial life. Environments like Earth's deep ocean vents host hardy organisms that survive without sunlight. A parallel process could occur under Ceres' crust. Instruments on Dawn also detected ammonia-bearing clays. Ammonia lowers water's freezing point. It can allow pockets of liquid to persist even in harsh conditions. These findings line up with the possibility of cryovolcanism, where water or slushy brines seep through fractures and erupt onto the surface. Such activity would create chemical gradients. On Earth, life thrives in regions with steep gradients feeding on chemical imbalances. Many questions remain. Did Ceres lock away liquids eons ago, or do active processes still recharge hidden reservoirs? Future missions might carry landers or impactors to probe the crust. Samples returned to Earth would unlock new data. Observations of surface chemistry could reveal organic compounds vital for life. Neptune's largest moon, Triton, is a world of intrigue. Voyager 2 observed geysers erupting from its surface, suggesting subsurface activity, possibly driven by tidal heating. Triton's retrograde orbit and young surface hint at a dynamic interior, potentially harboring a subsurface ocean. Triton circles Neptune in a retrograde path, a rarity among large moons. Observations from Voyager 2 revealed icy plains and strange black streaks across the surface. Cryovolcanic plumes expel nitrogen frost, which points to internal heating driven by tidal forces. That internal energy can warm subsurface layers, allowing liquid water to persist under a frozen shell. Ammonia-laced ice on Triton's exterior indicates chemical pathways linked to habitability. Surface temperatures drop lower than most locations in the solar system. Despite those conditions, an ocean concealed beneath kilometers of ice remains a possibility. On Earth, microbial life endures in lakes sealed under glaciers sustained by chemical reactions and slight heat. A similar process might occur inside Triton, where salts and other dissolved minerals could create energy gradients. Small amounts of warmth can power metabolic reactions even in a frigid environment. Clarity on Triton's internal chemistry could transform perspectives on life's boundaries. Among outer solar system bodies, Triton presents a compelling case for ongoing activity, organic building blocks, and hidden water far from the sun's warmth. Ganymede also stands apart for possessing a magnetic field, a feature rare among moons. This magnetic bubble protects the interior from charged particles in Jupiter's radiation belts. Such protection increases chances for stable conditions. Other forces come into play as well. Tidal interactions with Jupiter generate internal heat, which may support water in liquid form. Current and upcoming missions plan to refine our perspective on Ganymede. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, will analyze the composition and structure through advanced imaging and radar. Researchers hope to uncover clues to the depth and salinity of the ocean. The answers could reshape theories on how life evolves in extreme environments. Ganymede's immense size, buried seas, and magnetic shield inspire a sense of promise. This moon challenges old assumptions about where life can exist. Each orbit around Jupiter delivers a chance to explore chemical and thermal processes that drive evolution. Ganymede's subsurface ocean offers a stage for the study of alien biology, and future missions may reveal a hidden population thriving in darkness. Once considered the ninth planet, Pluto looms on the solar system's outer edge. But instead of a frozen husk, NASA's New Horizons mission uncovered a dynamic realm. Images showed icy mountains, nitrogen glaciers, and smooth plains. These features pointed to recent geological activity, implying an internal heat source. Beneath a thick crust of ice, a subsurface ocean might endure. Liquid water, shielded from cosmic radiation, creates a possible habitat for life. Organic molecules blanket Pluto's surface. Methane ices give it a reddish hue, hinting at complex chemical processes. Life on Earth survives in places without sunlight. Microbes cluster around chemical vents or inside thick ice. A similar ecosystem could evolve in Pluto's hidden ocean, powered by chemical gradients and mild internal heat from radioactive decay. Cryovolcanoes and glacial flows on Pluto indicate active reshaping of the terrain. A sparsity of impact craters signals resurfacing. Liquid pockets near the core may exist, warmed by geological forces that prevent total freezing. Water plus organics equals a powerful cocktail for biology and thus the possibility for life on Pluto. Pluto, like the other fascinating planets and moons in our solar system, broadens perspectives on life's potential beyond Earth. It demonstrates that active worlds can thrive far from the Sun. If organisms exist there, they reveal an astonishing ability to adapt under conditions long assumed too harsh. The secrets concealed beneath Pluto's shimmering ice beckon, and the next wave of exploration promises to peel away more layers of this distant enigma. The search for life in our solar system is far from over. Each of these destinations, Mars, Europa, Enceladus, Titan, Venus, Ceres, Triton, Pluto, and Ganymede, offer unique clues and challenges. As we continue to explore, we may find that life is not confined to Earth, but is a common thread woven through the fabric of the cosmos.
Thank you for watching Xenofeed, News of the Outworld. If you enjoyed this video, please remember to like, share and subscribe. Click the bell to be notified when Xenofeed posts new, thought-provoking content. Xenofeed.